All right, let's get started. So Ethereum deep dive. We're going to talk about networks in Ethereum. We're going to talk about transactions and the life cycle of a transaction. And we'll talk about the concept of gas that you were first introduced to yesterday and how the economics of that work. Quick recap. We did two things yesterday. The first was send each other cryptocurrency using Metamask. And we used what was called a testnet. You guys use the Robston testnet. The image on the left here is probably what you saw. And you may have observed that there were a few interesting properties here, fields for you to fill out, the gas price, gas limit. And based on that, MetaMask told you a transaction fee that it was going to charge you expressed in Ether and conveniently portrayed also in USD. And then you submitted the transaction, you signed the transaction, and the transaction took some time to be processed by the blockchain, to be validated and propagated. And then the recipient of the funds confirmed for you that I have received the funds. That was the first exercise we did to give you a sense of how you submit transactions. The second exercise was we coded up a simple cryptocurrency. And the basic idea for cryptocurrency is you manage account balances and you allow people, you create some liquidity for some digital asset, which in memory is just a list of balances for starters. You can add much more functionality to that. But for starters, it's just maintaining balances and changing those balances. So you built that as a contract using Solidity, using Remix, which is an IDE. An IDE is a development environment for, and in this case, for Solidity programming. And this particular IDE, Remix, allows you to deploy contracts right from within that environment. And you deployed, I think we only deployed to a virtual machine yesterday, right? We did not deploy them to a proper blockchain outside. Yeah. I want to start with a review of concepts. So some questions I got were, hey, what's a testnet? What is the JavaScript VM? How does it differ from a blockchain? What is gas price? How does it work? We will talk about that in this session. Then I got a really interesting question about, hey, what is the relationship between nodes, accounts, blocks, transactions? I think yesterday you were inundated with new phrases. And so I want to break those down for you. We'll do that pretty quickly, but we'll do it right in the beginning. So let's start with that second question. Nodes. Anyone? What's a node? It's a physical system. My laptop can be a node. When does it become a node? When it joins a blockchain network. So currently, the current implementation of blockchain systems is that they are connected peer-to-peer. I think Abhishek told you about this as well. What does it mean to be connected peer-to-peer? It means every node is connected to every other node, which is full redundancy. It has good properties, it has horrible properties about efficiency and speed, and Rishabh will tell you about some of those and how we can get around them in business use cases where transaction speeds matter. So a node is a system. Okay, it's a system connected onto the blockchain, and it participates in maintaining, in first of all, hosting the blockchain, and second, maintaining the security of the blockchain. How does it do that? It participates in mining. It participates in validating transactions, in broadcasting transactions. Make sense? If you were making your own blockchain system, the coding would be much more complicated than what we are doing right now by building on top of Ethereum. You would be coding at the peer-to-peer protocol layer. We conveniently are building on top of Ethereum, which already handles the peer-to-peer networking for you, talking between nodes, broadcasting messages. You would be coding that yourself. Bitcoin's first implementation had to be coded from scratch. Ethereum had to be coded from scratch. And this is not the end, this is just the beginning. Blockchains continue to come up. Different teams out there are researching, developing different architectures of blockchains. A node is a participant in a blockchain network. Now, what is the blockchain? What are blocks? Each node has a copy of the blockchain. A blockchain is a chain of blocks. Okay, that's what's visualized here. What's in a block? Can anyone tell me? Transactions. Okay, let me actually create a new concept for you. Transactions are an action that you do. Ethereum is often described as a state machine. Does anyone know what a state machine is? A state machine maintains states and allows that state to change through transitions. What is a transition in this case? It's a transaction. The block represents the system state at any given point in time. The state itself can be thought of as this concept of accounts and some associated data with those accounts. This is the relationship between accounts, state, blocks. A block represents a state in the system. And that state can be captured as, hey, we have accounts in the system associated with people as well as with contracts. Each of them has some data, balance, for example. That state changes with transactions. So when I sent one of you Ether yesterday using Metamask, that was a transaction that changes the state of the system. Ethereum is a state transition system, a state machine. All right? So that was a recap. I hope the relationships between the different concepts are clear. Let's talk a bit about Ethereum from a layperson perspective, understanding so yesterday we spent a lot of time on the technology, like the nitty gritty, both with Bitcoin, and then we extended Bitcoin to talk about Ethereum. Let's just approach it top down now, understand what does it really look like. So Ethereum today is a network of nodes that are spread out all around the world. Specifically, there are 16,000 to 17,000 nodes, and that number can change as nodes join or leave. Nodes join because they can make money off of joining from mining, and they leave because they're not making enough money or the cost of electricity is too high for them, etc. There are different reasons. They manage their own economics. So nodes participate in maintaining the network. In Ethereum, in the public main chain, there are 16,000 to 17,000 nodes spread across 6 continents. The blockchain has grown quite long. I was sitting here checking Etherscan, the website I told you about, to see what's the latest block. And a few minutes ago, it was 5,878,984th block had just been added to the blockchain. I'm conveying all of this to you because I want you to have an appreciation for how big this is in terms of how many people are involved here, how much data is involved. The reason people are so excited about blockchains is they're real, first of all. They're touching a lot of lives, and they're just a novel concept because of the computer science, the mathematics, the economics we saw yesterday. And this is just the beginning. I can't reiterate that enough. The technologies themselves might change, the economic protocols might change, the cryptography we might have breakthroughs there. But this is the state of Ethereum today. Let's talk about a topic that I think will set the stage for Rishabh's talk on different flavors of blockchains and why some are better than others. Ethereum right now can process about 15 transactions per second. And this is from a few months back, a figure quoted by Vitalik, the founder of Ethereum. And so 15, do you guys know, for those of you who come from a business background, think about your operations class. Those of you who come from a computer science background, think about a networks class. The concepts of throughput and latency. Okay, this is what we're talking about here. Can anyone tell me block time versus TPS, transactions per second? Which one is throughput? TPS is throughput. This is an MBA course topic. Block time is your latency. How long does it take for a new block to be added? They're different concepts. I'm mentioning that because it so happens for Ethereum, they're the same number, and I didn't want you to think it's the same concept. If you look at Bitcoin, it's far slower. 2 to 3 transactions per second. And for an individual, from a micro perspective, if I want to get a Bitcoin, if I send you Bitcoin, if yesterday I'd sent you Bitcoin on the mainnet for Bitcoin, it would have taken a while, 10 minutes. And when you work with exchanges, if you buy, sell Bitcoin, it takes even longer than that because they have their own latency on top of the network's latency. These are problems. Why are they problems? Because, hey, we on one hand talk about financial systems being built on blockchains. On the other hand, blockchains are not able to keep up with the pace that is needed. Now, what's the pace that's needed? Let's look at some comparables. PayPal, 450 transactions per second. Visa, over 50,000 transactions per second. Blockchains need to improve quite a bit. And that is why there's so much money going into this space. At the blockchain level, I'm not talking about ICOs now. I'm talking about money going into new blockchains. There are new blockchains coming out every week. In fact, the blockchain world describes Bitcoin as a first-generation blockchain, Ethereum and Neo as a second-generation blockchain because it adds the capability to publish code, smart contracts to have a complete language, and third-generation blockchains, which include Cardano and a number of others, which are trying to bridge the best of all worlds. The flexibility to write any software, the scalability, the transaction processing times of existing financial networks, all of these things. In the blockchain space, there is a concept of a trilemma. It's like a dilemma, but with three things. And this, I think, this was coined by, again, Vitalik, who brought Ethereum into the world. And Vitalik calls it the blockchain trilemma, as in this is not just a problem for Ethereum, it's a problem for public blockchain systems. You have to choose what you want. We talked about the security of blockchains. We talked about decentralization. Decentralization refers to having a wide distribution of nodes among different owners. So, for example, Ethereum is the most decentralized blockchain out there with 16,000 to 17,000 nodes, as we discussed. And then there's scalability, which we talked about in the last slide, where all blockchains today are not meeting the needs of the financial system, at least. They can meet the needs of some systems, not all systems. And what Vitalik said about the trilemma was, hey, you have to pick 2 out of 3. You guys have probably seen other trilemmas in life. I think when I was at MIT, there was a trilemma we used to talk about. It was study, play, or sleep. You can't do all 3, you have to pick 2. And so I think you can guess what we all picked. So the blockchain trilemma is you have to pick 2 out of 3. And for now, all I want to say about this is their trade-offs. And current blockchain community has chosen decentralization and security as primary objectives that cannot be compromised. And what they're trying to do is figure out what compromises are acceptable. For example, a consensus protocol that maybe rather than needing 51% collusion for an attack, needs only 33% collusion for an attack. That's a compromise on the security aspect, but with the benefit of added scalability, speed. This is an ongoing discussion. So I don't have a solution here personally, and I think that there isn't one in the market yet, but many people are working on it. And a lot of the blockchains that have raised millions to billions of dollars are working on exactly this problem, which is how do I build a better blockchain solution that reaches a better compromise on this triangle, does better on scalability with a compromise on decentralization and security that is still serving our needs as a society for both business use cases as well as consumer public use cases. Types of networks. I think by now you guys have understood this. There's the concept of a personal network. The JavaScript VM we use is a personal blockchain. It runs in your system. When you restart your system, it restarts. If I have a blockchain running in my browser, when I restart my browser, it restarts. The accounts exist only in that system. No one else can talk to it. It's closed off to the rest of the world. It can be really great for testing. The advantages there are, hey, you don't need to go to a faucet the way we did yesterday to get Ether. You can just initialize your account with Ether. That's why you saw when we set up a VM yesterday, a JavaScript VM with accounts, we each started with 100 Ether, which is a lot of money. That's just free. You can do that. You can initialize your blockchain with whatever initial balance you want. We'll be using personal blockchains for most of today. A private blockchain. That can mean any number of things. Ethereum, for example, is a piece of code. It's a protocol. You can run that code and you become a part of the network. You become a node. What if Rishabh and I said, hey, we want to run a private blockchain between the two of us? We could still do that with Ethereum. You can also do that with the technologies that you guys mentioned. Someone mentioned Hyperledger. Hyperledger is being built for the enterprise use case, and you can initialize a private blockchain. What does public versus private really mean? Private means that every person who joins only because they were invited to join or they're authorized to join. So private blockchains typically have some centralization. Some admin invites or authorizes or whitelists who can be a part of the network. Rishabh will go into details on how that works. Public is what we've been talking about. Ethereum Mainnet. So there are two flavors of public chains. Ethereum, the one I showed you with the map, 16,000, 17,000 nodes, that is the main network. Money on that is real money. You can take that Ether, you can take it to an exchange, you can get rupees for it, you can get dollars for it. Because people have ascribed value to it. A testnet is also public. I don't know how many nodes there are in the test network. I didn't check. You can check. It's for test purposes. We talked about the value of testing yesterday. One is money. You don't want to work with real Ether when you're testing a contract that isn't yet finalized. It might have mistakes. You don't want to use real money for that. So you use fake Ether on a fake but public blockchain, which simulates the real environment of Ethereum. And it's faster, not always, but sometimes. And it's cheaper and it's more secure. Even if you lose your Ether there, you're losing your fake testnet Ether. The Ether that we got from a faucet yesterday was testnet Ether. That's why these faucets exist. I wish there were a faucet for the mainnet. That'd be cool. Okay, I want to talk to you about what we did yesterday, which is talk to a network. When you want to send someone cryptocurrency, you have to participate in the network. Is that true or false? You have to be a part of it, right? Otherwise, how is money leaving your account, going to another account? How is the transaction being proposed? So talking to networks does require you to somehow be a part of the network. And the original way of doing that is to run a node yourself. You can download the Ethereum source code, run it on your machine, and it will automatically start finding peers and start validating transactions. We did not make you go through that process because it's time-consuming, network-intensive, and many reasons for that. But you were still able to do it. So how did we do it? We went on to Solidity Remix, and we selected JavaScript VM from the options list, right? And what that did is it ran a blockchain inside our browser. So earlier, you have your browser's outside the blockchain. It's talking to a blockchain through a node that you run. That's what you have to do. This is what we did. Our browser simulates a blockchain inside the browser's memory. Everything is simulated. And our app is able to submit transactions to this blockchain in memory. So keep that in mind. When today we do JavaScript VM, this is what we're doing. All right? There's one other thing we did. We send each other cryptocurrency, and that was not using a VM because we needed to talk to other people. So we did that on a testnet, which is a public network. How did we do that? Did we run a node? No, we didn't run a node. So there's another way to talk to blockchains. That's where Metamask comes in. So you guys use Metamask. You remember that? And Metamask, you configured it to be set to the Ropsten test network. You remember that? You created an account on it. When you did that, when you typed in a password, it automatically created an account for you on a public blockchain. How does it do that? Well, MetaMask is doing the hard work for you. MetaMask is able to talk to a node that is a part of a blockchain. Okay, that's this node right here. There's something known as the Infura API, and what this is, it's a facility that runs nodes on the blockchain and provides an API to other people to be able to submit transactions through the API to this blockchain. So this node is not technically run by the MetaMask people, but MetaMask talks to this node, and MetaMask is a Chrome extension, which is the easiest thing you can use, and that's why they made it as a Chrome extension. Your apps that run in your browser that we will be making over the rest of the course are able to talk to MetaMask, submit transactions through MetaMask. They can sign transactions through MetaMask. And what that does is avoids the hassle of having to do this. Okay, and that's what I want to communicate here. And the way you select MetaMask, it's not called MetaMask, it's called injected Web3. I'm going to talk to you about what Web3 is later in the day. For now, you need to know that when you select this, Remix, or the apps that you make will start looking for some available node available locally, not the private VM, and they will see that there is something known as MetaMask that's available and accessible in the browser. So it doesn't say MetaMask here because there are other ways of doing this as well. MetaMask is one of them, but it finds MetaMask and it connects to the node that MetaMask talks to. And that's why when you connect, it starts showing you here that I'm now connected to Ropsten. And this is the flow. This is a testnet. There are 3 testnets out there. Ropsten is the one that most closely resembles the Ethereum mainnet in terms of its protocol. It is a proof of work network. It very closely resembles the Ethereum mainnet. Okay? All right, moving on. The rest is going to be a recap again. So we've talked about this. There are 2 types of accounts in Ethereum. Both of them have addresses. They look the same when you just look at the account address. There's an external user account. People like you and me, when we create accounts on Metamask or any other wallet, that's what we have, and a contract. And these addresses are designated with that 0x string, hexadecimal string. Let's talk about some of the features. External user accounts can have balance, so can contract accounts. You know, in an ICO, as we will and did implement a crowd sale yesterday, a contract can receive money and hold on to that money. So they can have Ether balance. The important thing I want you guys to get from this slide, the one important difference is a transaction can only be initiated in Ethereum by an external user account, not by a contract. Okay, so a contract cannot randomly initiate a call to another contract. It has to be initiated by an external user account. So when you send money, you are initiating a transaction. That's just a value exchange transaction. When you are calling a function on a smart contract, your account is initiating it. So message.sender in Solidity is your account. You are the initiator of the transaction. That's the one important difference between these two. The external user account has a key pair. MetaMask takes care of storing that for you, so you don't have to. Back in the day, people who got into Ethereum and Bitcoin early, like the guys who got into it or the girls who got into it 2010, 2011 for Bitcoin, they had to do a lot of this stuff themselves. And then we started having others building tools for the community to grow. And many of these tools are built by the Ethereum Foundation themselves because they have a vested interest in seeing the growth of the Ethereum platform. Contracts can obviously have code. External user accounts don't have code. All right? We focused a lot on two types of functions you can implement in your Solidity code on a smart contract. One was a function that creates a transaction, and the other does not create a transaction on the blockchain. The other is called a call, and you can designate that using the view modifier or the constant modifier in your function signature. The difference here is transactions change the state of the network. Because of that, they are expensive. They take time as well as money to run. And one important piece that you haven't seen yet, but you will see today, when I submit a transaction, it doesn't complete immediately. So if it changes the state of the system, I don't get that new state. There's no concept of a return value. Functions in other programming languages have a return value, right? A transaction has to propagate through the network, and so cannot return immediately. Keep this in mind. We're gonna think about this a lot today. What it does tell you immediately is, hey, I have submitted the transaction to the blockchain. Here is the hash of that transaction, of that signed transaction, also known as a transaction ID. And MetaMask shows you that hash. Remember, we went to Etherscan to explore the status of our transaction. The only thing we knew about it was a transaction ID. The URL even had a transaction ID on it, and then it said pending, because the state hasn't yet changed. So that's a very important piece to know. You don't get a return value from this function. You get the return value is the transaction ID, the hash. With a call, however, when you say get, you get the value instantly. So here if my code says return stored num, I get that instantly. All right? Let's move on. This is the slide I'll send out on Slack because I think it's important. Even when I was learning about how stuff happens under the hood, I found it useful to just internalize this. So we're gonna walk through it. This is the life cycle of a transaction. Let's say you build an app, and in this case, let's say the app is your Metamask browser, your Metamask Chrome extension in your browser. We're using it to send money. For now, let's just say we're sending money. Let's go through the transaction of sending money at the conceptual level. You guys have seen it, how it actually works. Let's go through it conceptual level. So the first thing that happens is the app has to create a transaction object. We won't talk about what is in that object, but you saw some of the fields that go inside it, and you'll see them throughout the day. That object, it just has its keys and value. There's other fields as well. So you create the transaction object. Then I told you that MetaMask was signing your transaction for you. It didn't ask you to do any hard work. When you hit submit, it automatically signs it for you. That transaction has to be signed. Once it has been signed, the transaction ID can be constructed because the ID is the hash of the signed transaction. So for those of you who are not able to read, that's the first two boxes. And this is what you get as a return value, or you can get as a return value if you want to. This is before I've even entered the blockchain. If you guys cannot see, there's a gray box right here. with the blockchain. Do you see blockchain written here? I think the visibility might be impaired for the people in the back. We'll put these slides up. Everything to the right of this line is on the blockchain. So everything to the left of it is not on the blockchain. And blockchain here demarcates where the blockchain starts. Sending transaction is where blockchain starts. I send it to the blockchain. Before that, everything is in my browser, it's on my computer. I have instant access to it. So transaction ID, as soon as I sign it, I can get that instantly. And we will use that property. Why will we use that property? Think of this as your identifier for the transaction that you can use to poll the blockchain and query its state at any given point in time. You saw Etherscan, that web app that tells you the state of your transactions. How does it do it? Well, it knows your transaction ID because that's what you typed in the URL. And it keeps asking the blockchain, hey, how's this going? How's this going? Has a transaction propagated? How many confirmations? And it keeps updating its UI. That's described here. This is the polling. Polling the state of your transaction on the blockchain using your ID. If you don't have an ID, what are you polling for? This is why we need a transaction ID. And so what we do is we compute a hash. And that transaction ID is also going to be on the blockchain. So you can follow that transaction throughout its life cycle. Okay, so you generate the ID. This is all off-chain. Now starts the part where it goes onto the chain. It's submitted. If you ran a local node, you would submit it to your local node. If you don't run a local node, hey, Metamask will submit it for you to the API that it uses that does run a local node, the Infura API. Transaction is submitted to a blockchain node. And at this point, what needs to happen is it needs to be broadcasted to the other nodes. So you have your local node, and it needs to be broadcasted to other nodes. I'm going to go back a couple slides just to show you. The local node is the one highlighted in orange, and then that needs to be broadcasted to the peers. So that's what we're talking about there. Now we enter the world that Abhishek was talking to you about today. Any number of nodes can receive your transaction. They will try to mine it. And so that's what it means by transactions picked up by the miner node. And it tries to add it to a block. You learned yesterday about the proof of work puzzle that needs to be solved. Let's just fast forward through that process. Let's say that it takes time, as you've seen. Let's say that one node out there has solved the proof of work puzzle and has found a valid block. Now that valid block needs to be broadcasted. Earlier, the transaction was broadcasted. Now a miner has found a valid block, broadcast that valid block to other nodes. This is where the verifications happen. And Etherscan, the website we went to, is showing you how many verifications happen. So transactions mined, the block is broadcasted, received by other nodes, and this is where code execution happens. So once the other nodes receive that valid block, they see inside it, does this have any code that I need to run on my virtual machine? If I need to run code, then I run it, update the state locally. And you can imagine this is why it takes so long, which makes blockchains challenging and fun to work with. Which means that if you want to know the result of your transaction, we need to find a way to constantly poll the blockchain and check when is that state updated. And when it's updated, tell our app that, hey, the UI needs to be updated. The libraries we use today, Truffle, respectively, and Web3, they handle a lot of this for you. The polling logic, we won't implement it. Polling is not trivial. We would have to do some interesting things there. So we will use libraries that do the polling for you and automatically tell you when it's done so that you can use the updated state in your UI. Let's talk about the final topic, which is the economics of executing code on Ethereum. This is an interesting point because we talked about how there's economics in game theory in blockchains. We need to find a way to incentivize nodes to not just mine and validate blocks and sending of transactions. We need to incentivize them to run my code. If I publish a smart contract, what's their incentive to run my code? And that incentive needs to be proportional to the amount of work that they have to do. Do you guys agree with that? Yes. This problem didn't need to exist for other types of blockchains that don't have a complex Turing-complete programming language. Ethereum needed a way to incentivize nodes proportional, not to the size of the transaction data, but to the work being done. So the big question in system design for Ethereum is how do you construct an incentive system that charges more when more work is done? How do you know that more work is done? Let me present a scenario that might break a very primitive version of Ethereum. So if Ethereum just said, hey, when a transaction comes in, look at how big it is. Look at the code file, see how many bytes of data are in that code file, and just pick a fee based on that. Let's say I create a very small code file with an infinite loop. An infinite loop, you guys know what that is? It just keeps running. The size of that code file is quite small. Some other person has a code file which is much bigger, but there's no loop. It just does a couple of things. Which one is more work? Small one, infinite loop. In fact, it's never ending. Ethereum needed a way to, first of all, make this impossible. And second of all, to charge this person, let's say it's a loop that runs 10 times, to charge this person more and to know that this is more work than this long file, which is less. So you can't just go by the size of the code in terms of bytes. When you submit a transaction, you submit the code along with it. You can't just go with that. You need something that uses work done. Now we have this virtual machine. Work done on this virtual machine can be calculated by, hey, which opcodes, which instructions are executed. And what you can do, what Ethereum does in fact, is it sets a price for each type of instruction. So let's say an instruction like an if statement has a certain price. Updating an integer has a certain price. Returning a value has a certain price. Calling another contract has a certain price. It's a very granular system, and if you go onto Google and you search gas costs of different instructions in Ethereum, you'll find a table. It's in the Ethereum yellow paper, not in the white paper. The white paper describes a high-level system design of Ethereum. If you look in the technical yellow paper, which is insanely technical, they tell you the gas cost. Gas, we haven't even defined gas, but they tell you the cost of each instruction at the instruction level. Gas is called gas because it is a fuel for the system. It is an economic fuel for the system. You need gas to run your car. Ethereum needs gas to incentivize miners to let things move forward for the blockchain to grow. That's why it's called gas. And it doesn't matter at the code level what your cost is. What ends up mattering is how much cost ended up being used at the VM level. Once I executed your code, how much work did I have to do? And I'm going to charge you based on that. You will notice that when you get a transaction going through its entire life cycle, it will tell you in the data that you can fetch from the blockchain, gas used. Today, when we start doing this full cycle, you'll start seeing not just gas price, but gas used when you get a transaction coming back. Gas used is, hey, how much work did I actually do? Multiplying the number of instructions times the cost of that instruction and adding it up. Make sense? At the VM level. When you have gas used, you can then multiply it by gas price, which is how much was this person willing to pay. Miners will have a choice of how they want to pick which transactions they prioritize. And as you can imagine, miners pick the ones where the person submitting the transaction is willing to pay a higher gas price. Right? That's a pretty good deal for me as a miner if I get paid more for a given unit of gas. Okay, but there's a balance to this as well. It can only go so high because there's a limit to how much overall work can be included in a block of transactions. And so if you set it insanely high, miners won't look at it. Now, because I'm not a miner, I haven't tried finding the ideal equation for me for how I pick gas price, but most miners sort their transaction pool by gas price. When you see a transaction fee in Metamask, it is the product of these two numbers. That is the end of this presentation, and that is your Ethereum deep dive. All right, thank you.